We will end the module on non-inertial reference frames by tying back what we have done to an earlier result that we found at the very beginning of the semester regarding motion in polar coordinates. So recall that in polar coordinates, Newton's second law has a somewhat non-trivial form. Specifically, we get that the force in the r direction looks like this, and in the phi direction, so this is a result we found very early on. Okay, I'm going to actually move this over to the right hand side here. Okay, now let's look at Newton's second law in a coordinate system, but let's do it while also doing some rotation. Okay, so to do that, I'm going to introduce two coordinate systems. We have one coordinate system here. This is the non-rotating coordinate system, S. So S is inertial. And then I'm going to take another coordinate system here, which we will rotate. Actually, I'm going to rotate in that direction. And this is the prime coordinate system. So I'm going to call it S prime. And they overlap. I'm going to put the origin of the two coordinate systems in the same place. Okay, so those are our two coordinate systems. They're also going to be a point here that we're interested in where some mass is located. Now, this is going to be determined by polar coordinates. So we can either do this in the non-rotating frame, where the polar coordinates are r and phi, or in the rotating frame, where they're going to be phi prime and r prime. So S prime is non-inertial. Well, actually, more specifically, it's rotating. And what we're going to do here is we're going to choose the rate of rotation, omega, to be equal to phi dot at time t equal t0. So in other words, this is only true at t equals t0, not at any other time. This means we can take omega to be constant. However, phi dot does not have to be constant. So we can have phi double dot is different from 0. So this has some interesting consequences. First of all, we can say that because omega, the angular velocity connects the two frames, is a constant, we can say that phi double dot is equal to phi prime double dot. Also, because both S and S prime have the same origin, we get that R equals R prime. And moreover, we get that R hat and phi hat are both going to be equal to R prime hat and phi prime hat. That makes it very convenient to express vectors in the two coordinate system because you have the same unit vectors. Note that that's not automatically true just because you have a rotating frame with the two origins being the same. So for instance, x prime and or x hat and x prime hat are obviously not the same, quite clearly because the x coordinate axes are not parallel. But that's parenthetical. This is what we're going to use. Oh, and also because we picked omega equals theta dot, that means that in the prime coordinate system, in the rotating coordinate system, motion at this particular time, t equals t0, is purely radial. In other words, we have that phi prime dot at t0 equals 0. And that's quite important, and that will simplify things for us. Okay, so I'm going to box these over here. We have those facts ready when we need them, which is going to be very soon. Okay, I'm going to drop this color code here because it's a little annoying to keep changing colors back and forth. But what we will have is that in the prime coordinate system, in the rotating coordinate system, we have that the force plus the Coriolis force plus the centrifugal force equals m times the acceleration. That much is clear. Because we are in a rotating frame, right? So we have to have those components present. I'm now going to write down the centrifugal force. We found that earlier. That's just equal to m omega squared r hat. Or technically it's r prime hat, but those are both the same because we have the same origin, right? So that makes things easier. The Coriolis force that's 2m r prime dot across the vector omega. Now, because we are in this rotating frame, in fact, this rotating frame is at this particular moment rotating with this object. For that reason, this is often known as the co-rotating frame. So this is the co-rotating frame. Because we are in the co-rotating frame, the motion is purely radial. Which is also expressed by this fact here, right? There's no change in the angle. Phi prime is, at this particular moment, in any case, not changing. So because it is purely radial, we can take r prime dot, so the vector r prime dot, that's going to just be equal to r prime dot r hat. It is just simply moving in the radial direction. And we also know that the vector omega is omega in the z hat direction. So we can then calculate what the Coriolis force is going to be equal to 2m r dot prime omega times r hat cross z hat. Now r cross z, that's minus phi hat, right? So for that reason we get that the Coriolis force is minus 2m r dot. I'm going to drop the prime here because again r and r prime is the same. The radial distance is the same in both coordinate systems. So that's the Coriolis force. And the centrifugal force. Right, so now what we want to do is reformulate. That's really what we want to do. We want to reformulate Newton's second law here on component form. So you want to write it down on component form, and to do that we need all the pieces on component form. We have the force, of course, is just Fr f sub r, f sub phi. We found this on component form here. What's left is the acceleration. Now the acceleration in polar coordinates is given by this. Right? So in general, the acceleration in the r direction has this form, and in the phi direction it has this form. However, in s prime, like we've said, phi dot equals to 0. That means I can say that the acceleration here is going to be just r double dot in the r hat direction. Right? That's this component. This one does not figure since phi dot is 0. And then it's r phi double dot in the phi hat direction. So let's now put all these three things together. We have the centrifugal force, the Coriolis force, and the expression for the acceleration into two equations. Right? One in r and one in phi. So we get f sub r, and the Coriolis force has no r component. So we just add in m omega squared r, and that's equal to r double dot, right? Zero component of the acceleration, times m. And then in the phi direction, now there's no phi direction, there's no phi component of the centrifugal force, so we just get this. And again, the phi component of the acceleration is r phi double prime. So this is now the expression for motion in the rotating reference frame. This is true in S prime. Now over here we have what we found earlier. This is Newton's second law in the non-rotating frame, or in any polar coordinate frame that is inertial. I'm going to put this right next to the other one just for comparison. So this is true in S. Although of course we have used the same variables here. We have actually changed back into the variables in the non-rotating frame. So these two actually have to be the same thing. And we can see that they are, because omega equals phi dot. So we have actually a choice on how to do it, how to do things here in polar coordinates. We can either use a complicated acceleration and a simple force, which is what happens when we are working in a stationary polar coordinate system. Or we can work in the co-rotating frame, where phi dot is equal to 0. And then we get a simple acceleration, but a complicated force. And it's really just a question of convenience which one you use. If you're on Earth and rotating with your frame, then it's probably easier to use the co-rotating formulation. Otherwise, you might use this one. But it amounts to the same thing. What is centrifugal force in one case becomes a centrifugal acceleration, or centripetal acceleration in the other case. What is a Coriolis force here becomes a Coriolis acceleration. Both descriptions are, of course, completely equivalent, but we come about them from different perspectives. And as is often the case in physics, your choice of perspective doesn't matter. You arrive at the correct solution regardless.